Hi, everyone, and welcome back. So, we're going to continue on with our discussion of statistics, and I just really want to reiterate that this is not a statistics course. So, the purpose of this is really to help you review um, what some of these statistics means, maybe how they're calculated in some instances, because that can help in understanding what they mean. And then in turn, this will help you when you are reading research studies so that you can understand, what the researcher is really saying behind the statistics. All right, so let's get started. As always, take a look at the to-do list and take a look over at the learning objective. All right, so let's start our conversation with a commonly used statistic called the t-test. T-tests are commonly used in research, and they are often used when we have a pre and a post-test design, and you want to see if there's a difference in the means from pre to post-test. T-tests are used for hypothesis testing. So testing, in this case, you're testing that there is no difference, right? Um, if there is a difference, we reject the null hypothesis, um, and we're saying there is a difference in the means. So there are several types of t-test. A t-test, or technically called a student's t-test, measures or compares the means of two groups. It can be used in clinical settings when you're comparing a pre and post-test drug intervention. It can be used for when surveys are administered, so pre and post-test test that you're giving someone. There are a number of ways t-test can be used with either pairs of groups or whether there are two independent groups. So a paired t-test is used when there is one group of subjects with a pair of observations, such as a pre and post test or two sets of lab values for the same measurement. While an independent t-test is used when there are two independent groups of participants with observations. And in this case, you're testing and comparing the means between the two independent groups. All right, so now let's talk about correlation. Correlation evaluates the relationship between two variables and looks to see if variable A increases with variable B. Correlations look at the relationship between the independent variable and the dependent variable. For example, do attitudes towards food safety influence food safety practices? Correlation can quantify the strength of a relationship between the two variables, and correlation can be used with continuous variables. Correlations can be plotted on a scatter plot. Scatter plots are visual representations of the relationship between the two variables. Correlation coefficient is used to quantifiably describe the strength and direction of the relationship between the variables. 1 equals a perfect relationship. As the independent variable increases, so does the dependent variable. The closer to 1, the more true a relationship. The top left table is showing an R, or how we would describe correlation coefficient as an R equaling 1. This is a positive relationship. As X increases, Y increases. The top right table is showing an R of -1. This is a negative or inverse relationship. As X increases, Y decreases. We can also describe how strong the correlation is. So an R of 0.00 to 0.25 generally indicates that there's no relationship, while 0.75 or above shows that there's a good to excellent relationship. But the R doesn't tell us if this relationship is significant, only that there is some type of relationship. We can refer to tables to determine the significance of R, But more often, statistical programs are used to determine the value of R and determine the statistical significance of the results. Pearson's correlation coefficient and Spearman's rank correlation coefficient are two methods to analyze the correlation. Pearson's is used when both variables are continuous and normally distributed, while Spearman's is used when the data is ordinal. It's important to look at factors that may limit the interpretation and generalizability of the correlation. Correlation does not provide information relative to the differences in data sets, only that there is some relationship between the sets. So again, it doesn't tell us if it's statistically significant, only that there is some relationship. For example, hypothetically, we can say we are looking at the relationship between eating dark green vegetables and eating red-orange vegetables. We may see that there is a relationship between the two. As people eat more dark green vegetables, the amount of the amount of red-orange vegetables also increases. But we don't see the magnitude of this change, meaning we can't say that eating 5 or more green vegetables means someone will eat 5 or more red vegetables. We can only say that there is some relationship between the consumption of dark green vegetables and red-orange vegetables. In fact, there actually may be some third variable that's influencing this relationship, but a correlation coefficient isn't going to tell us that. Go ahead and click on the video icon on this page to see a great video about correlation and causality. This video is from the Khan Academy, and I've also posted a link to the video in this week's session content. So go ahead and take a look at that. So correlation cannot prove causality. It can only prove that there's some type of relationship. I've posted a story of Pickles' death in a jar in this week's content folder. This is a tongue-in-cheek example of why it's not appropriate to talk about causation when you're talking about correlation. Really, anything could be found to be related. We could just easily say that bottled water is causing us to be overweight, as the increase in bottled water follows the increase in obesity. So more statistical testing is needed to really determine what is the cause of this relationship. So not just that there's a relationship existing, but what's the cause of the relationship? All right, so a little activity. For this activity, find an article related to your research topic that discusses correlation. Figure out what test they used. What's the R? Is it statistically significant? Do the authors generalize the result? If yes, describe how. Describe what the results mean in layman's terms. In essence, I'm asking you, decipher the research for the general public. All right, welcome back. Now let's go talk about another type of statistic. This statistic is called regression. Regression is a powerful tool to perform analysis, not just of relationships, but predictive ability. With regression, we are interested in seeing how the relationship is predictive of an outcome. For example, can a person's attitude predict a behavior? I've used I've used regression to see if self-confidence in teaching food safety can be predictive of actually implementing good food safety practices. We could also use it to help predict the outcome based on exposure. The book uses the example of degree of burns a patient has in predicting the quality of life. So regression is really a great tool to look at the prediction of behaviors. In regression, the variables are labeled X and Y, with X being the independent or predictor variable and y being the dependent or outcome variable. So we are looking at how x predicts y. If we know the blood pressure, the y, of a group of people at age x in a small sample of 10 people, we could use regression to predict a person's blood pressure by knowing their age. By plotting the relationship of each person, we could see the data trend and how close the correlation coefficient fits to 1. As we discussed previously, the closer to 1, the more closely related the variables are and the stronger the relationship. Linear regression helps us to determine the line that best fits or describes the orientation of all the data points on a scatter plot. The line is called the regression line, and we have a formula that can help to calculate regression. So here we have the regression formula. Y hat, so that's the y with the little hat on top, called y hat, equals a plus bx, so b times x. A equals the y-intercept, the value of y when x equals 0. On a graph, it is the point where the line crosses through or intersects the y-axis. This value can be positive or negative depending if the line crosses the y-axis above or below the x-axis. B equals the slope of the line, or said differently, the rate of change in y for each 1 unit change in x. When B is positive, y increases as x increases. When B is negative, y decreases as x increases. If B equals 0, then there is no relationship and the line is horizontal. So the regression line, the green line on this table, is the predictive values for y at any given value of x. But the reality is that values don't always fit the line. They may fall above or below the line. The actual regression line for any unique data set is really the line of best fit for a set of data points and takes into account the error component, or the points below and above the line. We determine how useful the data is, how minimal the error is, by calculating the sum of squares of the error components. The smaller the sum of squares, the closer the data points are to the regression line. So again, the regression line is the green line. This is the predictive value of y at any given value of x. And we are going to determine the sum of squares. So the sum of squares is calculated by subtracting the predicted values, y hat, from the true value of y. Rarely would we do this by hand. Most often a statistical program will do the calculation, but it's important to understand what the sum of squares is or what it represents. The smaller the sum of squares, the closer the data points are to the regression line. So this light blue box really is the sum of the squares. So it's the, how far away is the data point, the darker blue circle, from that line. R is helpful in determining a relationship, but nearly anything can have a relationship. R can be used in simple linear regression when you have only two variables. And in essence, the R that you would get from simple linear regression would equal your correlation coefficient, your R from there. They would be one and the same. But if you have two or more variables, or for a more precise regression, R squared is better at explaining the variance. The book gives the example involving blood pressure and age. For the regression of blood pressure on age, how predictive of blood pressure is age? The R is 0.87. This tells us that there's a fairly strong relationship, right? Because it's above or it's higher than 0.75. And r squared equals 0.76. This latter value means that 76% of the variance in systolic blood pressure can be accounted for by knowing the variance in age. We have 76% of the information needed to make an accurate prediction. And there are some other factors that account for 26% of the variance. The standard error of the estimate is another way to identify the accuracy of the prediction. And I'll refer to standard error of the estimate as SEE. If the SEE is high, then the scores are widely dispersed around the regression line, and it means that there's a larger degree of error. If the number is smaller, it tends to indicate a lower degree of error. The formula for SEE is on the bottom of page 552 of your book. Again, most often a statistical software package will do the calculation, but it's important to understand what the number represents. If you're reading a study and you see that the SEE is high, then you know that there's a larger degree of error or greater chance that the numbers are farther away from the regression line and more largely dispersed. Analysis of variance is another method of hypothesis testing. And here we're testing the null hypothesis to determine if the relationship between x and y occurs by chance. If the null hypothesis is true, then there's no relationship and the regression line is 0. It's basically a horizontal line. If the null hypothesis is false, then there is a relationship between x and y, and the line is significantly different from 0. This test is useful when you have more than 2 samples. So you might have a pre, a post, and a follow-up. Or when the samples have different numbers of observations in each of them. So you have a different number of pre-tests or post-test or follow-up tests. ANOVA can be, so analysis of variance is often referred to as ANOVA. It can be one-way or two-way, which simply means it has one independent predictor variable, that's a one-way, or two-way when there are two independent or predictor variables, two or more. ANOVA is typically used with categorical data with groups or levels. For example, vegetables can be grouped into categories, dark green, red, orange, starchy, etc. Maybe you want to know if there's a relationship between types of vegetables and amount consumed. So an amount consumed could be measured categorically in levels, so a lot, a little, or nothing. And the seasons, spring, summer, winter, fall. So you want to look at the relationship between these three things: the type of vegetable, the amount consumed, and the season. ANOVA can help you understand if there is a statistically significant relationship between the categories of vegetables, the season, and the amount consumed. But not all data is linear. In fact, it can be curvilinear. And this is an example. So data can follow a J curve or a U curve. I'm sure there are other curves that it can follow. This is an example of a J curve for all-cause mortality versus BMI. So the title of this slide is Body Mass Index and Cause-Specific Mortality in 900,000 Adults. So this model shows that the relationship isn't linear, it's curvilinear. But there is indeed a relationship. Those that have high and low BMI have a greater risk of mortality. So low BMI on the left and high BMI on the right both have a relationship to mortality. ANCOVA, or analysis of covariance, is a combination of ANOVA, so analysis of variance, and linear regression. It's used to compare groups on an dependent variable when groups may differ on some covariate or some relevant characteristic or factor. So ANCOVA removes the covariate, the factor, where they differ, and provides a more valid explanation of the relationship between the independent variable and the dependent variable. There are some terms that are useful in reference to ANCOVA. Linearity of the covariate means that you must determine that there is indeed a linear relationship between this covariate and the dependent variable. They some way have to be related or show some type of relationship. Homogeneity of the slopes means that ANCOVA assumes that the slopes of the regression for each group are parallel. This means that the group must all have equal relationship with the dependent variable. If the slopes of the group are not parallel, then the groups have a different relationship with the dependent variable. Independence of covariate, or of the covariate, means that the covariate must be related to the dependent variable, but must be independent of the other independent variables. So it can't follow the same relationship. Interpreting ANCOVA can be a very good tool for controlling for covariates, but it can't control for poorly designed studies. So you may be able to control for these factors, these special factors, but you can't control if the study was not designed properly. Again, these terms and how to properly identify the information and calculate any of these statistical formulas that we've talked about will be covered in a statistics course. Again, it's just really about understanding, as you're reading these studies, what all this information means. All right, so here's an activity. Find an article related to your research topic that uses regression, ANOVA, or ANCOVA for analysis, and decide what are the variables that are being studied. Did the study show any type of statistically significant results? And describe what the results mean in layman's terms. So decipher the research for the general public. Okay, we're in the home stretch of statistics. So we're going to talk about our last statistic test, chi-square. Chi-square is a non-parametric test. Non-parametric means that the data doesn't necessarily fit a normal distribution. So what we've been talking to up to this point are data that fit a normal distribution. Non-parametric tests often use ordinal data. So remember that ordinal data relies on ranking and not a true valued number. Categorical values or variables can be ordinal. The chi-square test uses the frequency or proportion of the categorical or ranking variables for analysis. Chi-square is used to determine if there is a difference between the proportions observed and the proportions that are expected by chance. The underlying assumption in chi-square is that each category within the observations have at least one response or one frequency. If this is not met, then chi-square may not be an appropriate test. Chi-square uses a goodness of fit, and it compares observed frequencies with expected or known frequencies. Mendel's observation of P's is a perfect example of a goodness of fit model. So remember back to Biology 101 when they talked about eye colors. So Mendel compared the frequencies of specific color and shape of a theoretical distribution based on his prediction of the role of dominant and recessive genes. When the observed distributions matched the theoretical distribution, his theory was proven. Chi-square test the null hypothesis that the outcomes within each category will not specifically differ from the expected distribution, meaning the observed proportion will be random and happen by chance. A test of independence tests to see if there's an association or a lack of association between two categorical variables. The research question asks if the proportion of subjects observed in each category are independent of each other. Therefore, when the null hypothesis is rejected, it indicates that there is an association between the variables. So this is the formula for chi-square, and chi-square is typically represented by the x with the superscript 2. So chi-square is the sum of the observed minus the expected squared divided by the sum of the expected. As the difference between observed and expected frequencies increases, the value of chi-square will increase. Or if the frequencies are the same, then chi-square will be closer to or equal 0. So the question we are determining in calculating chi-square is, do we reject the null hypothesis that the two events are equal, and therefore say there is a statistically significant chance to get a different outcome? Let's do the math. Say we flipped a coin 100 times. Our expected outcome is 50 heads and 50 tails. But when we actually flip the coin, we get 47 heads and 53 tails. Now, let's do the calculation. So let's do the math. So taking our numbers, we observed 47 for heads minus the expected 50. We square that number, divide it by 50, and we get 0.18. We do the same for the tails and we get the same number. So the sum of these terms for all categories is the value of chi-squared. So we would add 0.18 plus 0.18 and we get 0.36. Without a computer program, we would need to go to a table to determine if this chi-square statistic is significant. Appendix table, I think it's A5 in the book, can help you determine if the test statistic is significant. So take a minute to grab the book and go to that table. In this case, with an alpha of 0.5 and a degrees freedom of 1, so degrees freedom is the number of categories minus 1. Here we have two categories, heads or tail, so the number of categories minus 1, so our degree freedom is 1. We would have a test statistic of 3.84. In order for this to be significant, the test value needs to be greater than or equal to the critical value of the table. 0.36, our test result, is less than 3.84 from the table. Therefore, the null hypothesis is not rejected. We accept the null hypothesis, and the chance of getting heads or tails is basically equal. There's no statistically significant difference. A contingency table is a visual representation of the counts for the data for the chi-square test. Let's say we wanted to look at those who had a car and whether they ate fast food or didn't eat fast food. Both are categorical variables. Car equals yes or no, and eating fast food equals yes or no. So we can do a chi-square. This contingency table gives a visual representation of the observed results. If the null hypothesis is true and there is no association between having a car and eating fast food, then we would expect to see the same proportion of those eating or not eating fast food in both groups of car owners. Meaning, of the 23 of those who have a car, 66% should eat fast food, and of the 27 who don't have a car, 34% should not eat fast food. So the expected would be similar to the observed. I've provided here how you would determine the expected frequencies. So I just want to reiterate again that most often this data is being input into a statistical program, and it is calculating these expected frequencies and then comparing them against the observed frequency. So I'm just providing this here for you to take a look at. It's not a stats class, so I'm not going to, you know, uh, I'm not going to test you on whether or not you know that, but at least you understand how and the data is manipulated or handled, and how you can and hopefully that will help you better understand when you're reading these research articles. The McNamara test is especially useful with pre and post test designs when the dependent variable is measured as a dichotomy in an ordinal or nominal series. So it's yes or no. So it's a 2 by 2, or what we would call a 2 by 2 tables. I show you this because this test can be useful in questionnaires that follow this model, so this model of pre or post test. So this is where I'm going to end the presentation. So for your last activity, find an article related to your research topic area that uses chi-square for analysis. What are the variables that they're using? Does it fit the chi-square guidelines? Are the results statistically significant? Describe what the results mean in layman's terms. So again, it's all about deciphering the research for the general public. What are they saying? So be sure to read the chapters, complete any assignments and activities that are due this week. As always, if you have any questions, be sure to reach out to me, and take a little break from statistics. Talk to you all soon.